Yep. Should be okay?
Okay.
Perfect. Sorry. Okay, so in Idris, types are just first-class member of the language, which means that basically we can use value into a types, just like in Vect, which is probably the most common example of dependently typed structure. So it's a length-based list of elements. So we have the length, the type of the element, and all of this form a type. But we can also return type as the result of a function. So this function takes a Boolean, and depending on the Boolean value, it will return a different type. And we can also use type as parameter for functions. And of course, we can just do computation in types of type signatures. So we can append a vector of size n, a vector of size m, and the result will be a vector of size n plus m. And we can also use the parameter of a function as a parameter of another function that will be used to compute the return time of a function. One of the problems we have with this is that with dependent type, it becomes quite complex to find out when we can erase type level information or not. For example, in this version of length, I don't make use of the size of the vector here. So basically, all my body doesn't care about the value of n. So n can be erased in this version of length. If I use this version, unfortunately, I use n here, so I will have to carry along the length of the vector at runtime as well. Fortunately, the second version of Idris provides a solution to this thanks to quantitative type theory. In quantitative type theory, you can assign three different quantities to resources. You have the zero quantity to say that a resource can't be accessed at runtime, the one quantity to say that the resource must be exactly used once at runtime, and unrestricted when you don't have anything to a value, which means that you can use freely your resource at runtime. You can use it or not. You do whatever you want with it. You can make a copy of it, whatever you want. Just like if you don't have any information about the resource usage. And by default in Idris, an explicit parameter is unrestricted, and a name that is implicitly bound is erased at runtime. What does it mean? On the length example again, here, access has no quantity assigned to it, so it's unrestricted. I can use as many copies of access as I want. NNA are implicitly bound, so they will be erased at runtime. If I change the definition of length for this one, here I assign access the quantity 0, so no, it's erased at runtime. I can't use access anymore. And no, n is explicitly bound, so I will be able to use n at runtime and to define length according to the value of n, for example. And the most common example for linear resources is a function that I can't implement in Idris because I only have one copy of x available, and I try to build a pair with two values of type A, which means that I should be able to copy x to implement this function, and unfortunately, I can't. Autoparameters and interfaces. Autoparameters is something that is very interesting in Idris because basically what it means is that you ask the compiler to find the value of a given type for you. So if I take the example of this index function, which will look for a value x in a vector xs, usually this kind of function would return a type maybe not, because either the element is in the vector, and in that case you will return the index, or it's not in it and you will return nothing. What you can do in Idris is saying to the compiler, well, find me a proof that x is an element of xs. So this arrow here means that it's an auto parameter, which means that Idris has to find this value by itself. So the compiler will go through the different constructor of the type and will try to find a constructor that match to the given value. If it can find it, the compilation will continue. If it can't find it, you will have a compilation error. And there's an alternative syntax for autoparameters. This one was introduced in Idris 1. This one was introduced in Idris 2. And in Idris 2, actually, you can use one or the other. It's exactly the same thing. No, interfaces. What we mean by interfaces in Idris is very close to what we mean by type classes in Haskell. And if you're not familiar with Haskell, it's somehow related to the concept of interface in any object-oriented programming language with a little twist. We will see this. So I can define an interface with a set of operations that is assigned to this interface, and I can later on implement this interface. So here is the equality defined for Boolean. And the difference with interface in an object-oriented programming language is that you don't have to define all the interface when you declare your type. You can define these interfaces on demand when you need it, actually. And when I need to use an interface, I have this syntax again. It's the same arrow as for the autoparameter because the mechanism behind the scene are almost the same for the compiler. So here I need to have this interface implemented to be able to use this function. I will detail a bit more interfaces because it's used a lot in the paper. So Idris expects to identify unambiguously the interface to use when it compiles a program, which means that you can have only one default implementation of an interface for a given type. But there's a mechanism to declare several interfaces thanks to what we call name interfaces in Idris. So this is the default definition of equality for pair when we compare both sides of the pair. But we can, for example, make another equality for pair, which will only compare the first element of the pair, and we give it a name, pair first EQ, and we can do the same thing on the second element of the pair. And when the EQ interface is required, we can pass a name implementation in our program. So we can do it as follows. This function here for equality doesn't say anything special, so it will use the default implementation, this one. But here we say that we want to use this name implementation, and here we will use this one. There's a lot more to say about interfaces. For example, we can pass something else than type as a parameter of our interfaces. For example, we can pass a NAT, but we can even pass an interface as a parameter of another interface. And it's used in the paper because it allows us to solve some ambiguity issues that we would have otherwise, and that can be solved this way. Can't enter into detail here because it's quite technical, but it's very useful in our use case. The last thing about interfaces, we have determining parameters. So here, for example, if we have the state interfaces, it has two parameters, the type of the state and the monad that will carry the state. And knowing the monad is enough to determine the interface to use without ambiguity. Last thing I want to talk about for Idris to understand the content of the paper is the metaprogramming facilities offered by Idris. Idris has an internal language called TT-imp that is used during the compilation, and you have a quasi-quotation mechanism that allows you to go from TT-imp to Idris terms and to go back from Idris terms to TT-imp. So there are two examples here where here I use this quotation to go back from TT-imp to int, and here I go back from int to TT-imp using the backquote. The problem with TT-imp is that it's an untyped language. The good thing is that we also have ELAB, which is metaprogramming facility that is typed. The name ELAB comes from elaborate because it was used first to elaborate proof, but we can use it to just do some metaprogramming, typed metaprogramming actually. So it comes with do notation. So here, for example, I get out of ELAB to get an int. I get another int from y, and I can add these two ints and put it back into an elab. We can build an elab out of a tt-imp using the function check that will be checked when we will try to compile the elab. And how do we compile an elab? There's two ways to do it. The first one is to use a macro directive that will compile the elab of type A into an A, and the other one is to use run elab. And similarly, you have an elab of type A here, and using elab, you will get the A out of the elab by compiling the program. That's it for Idris. A few references if you want to know more about Idris. We can move on now to the real content of the paper, which is dependent tagless final. So the context. It's the well-known issue of the expression problem. So this is the expression problem applied to domain-specific language. So basically, I have a base language, and I want to be able to add operation to it. I want to be able to add some interpreters to it. And in both cases, I don't want to modify the existing code, and I want to retain static type safety. In functional programming, there are two major approaches to address this issue. So there is tagless initial, which means that basically you represent your AST by its abstract syntax tree, and your interpreter just follows this abstract syntax tree to provide a value or a program. And you have tagless final. Tagless means that we don't carry any type information at runtime, and final means that the interpretation is the implementation of a denotational semantic. Tagless final, the interesting thing about it is that the initial proposition of tagless final was made using a dependently typed language by Ta and Al in 2001. But the seminal implementation of tagless final was provided by Karat and Kiselyov and Chan in 2009, and it doesn't use dependent types anymore. The reason was mainly that it's easier to adopt this paradigm without the dependent types, and an issue that we have with dependent type is what we have seen earlier, is that it was actually quite hard to figure out whether the type information will be retained or erased at runtime. So we have seen that Idris solves this issue thanks to quantitative type theory. So one of the questions we had was, okay, what if I try to implement tagless final with dependent type? Could I benefit from it? Could it help in some way when I try to implement tagless final? And we will see what happens when we do it. So first, let's begin with the tagless final implementation with almost no dependent type, but in Idris. So we consider three language fragments. A base language, so we have a way to introduce integers, to provide add and addition multiplication on integers, and or equality and if then else. We have a way to provide a read context, so a way to access a value from the context and a way to chain values. So we pass the result of the first expression in the read context of the second expression. And we have a third fragment that is basically a way to deal with variables. So lambda abstraction, application, and a way to get a value from the environment. We don't use De Bruijn indexes, but we use the name of the variable, and we resolved it with a bit of dependent type and auto-parameter in Idris. The interesting thing with this three fragment is that we see here that we have a zero quantity that is assigned to the tag of the expression, which means that in our interpreter, we will always erase the type information. The other interesting thing is that our base fragment doesn't require any information from the context, but the read fragment required the value that we can read from the environment, and this last fragment required a list of variables. So what happened when we want to build an interpreter for this fragment? This is an evaluation interpreter for the base fragment. I won't go into the details because it's quite trivial. This is an evaluator for the read fragment. And this is an evaluator for the variable fragment. And I passed quite quickly on these three interpreters, but if we look at their type, we see that they have a different kind. So they require different things. And the question is, how do we compose them? Actually, the problem comes from the definition of the interface themselves. As I said earlier, this one has required no context information, but this one required the type, and this one required a list of variables along with the type. And the problem is that it's quite difficult to find a way to compose these three interfaces. And what we do usually in this kind of situation in Tagless Final is to provide a unified version of the context. So no context is a list of variables, a read type for every interfaces. One of the problems we have with this is that in the context of the expression problem, it means that if we want to add another fragment that adds something else to the context, we will have to modify the existing interfaces, which is quite painful. So we try to address it using dependent types, and fortunately we achieved to address it. And this is the idea. The idea is to go from this definition of the interfaces to this one. So the idea is that we consider the context as a type variable, and we will define the type of context depending on the fragment that we want to put together into our language. What does it mean? For base doesn't deal with the context, so we just carry along an empty context, a context, and we don't do anything with it. So it's a very straightforward case. In the case of read and var, however, we will have some context manipulation. So in the case of read, we need a way to get the type of the variables that can be of the information that can be read from the context. So we will need this operation at the type level, and we need a way to set the type of the information that can be read. So we need this type level information. And how do we use it? In the interface that correspond to a language fragment, we pass the context, the interpreters that rely on the context, and we pass the implementation of this interface that express how we manipulate the context. And this implementation is called R. And as you see here, when I use the read function, the result of my function will have this type. So it will get the type of the read function from the result of the implementation of this function. And the same goes for the var context. How do we implement this in practice? So we start by instantiating the context. So if we want to implement all three fragments, we will have this as a type for context. And the implementation of the read context and the var context will be this one. And the interpreter now, the interpreter for read that use the read pair context implementation that was given here. And the same for var, where we use the var pair implementation. And we can just use this to resolve the type that will be provided by the context when we need it. So to summarize the approach, the idea is that we define the type level manipulation of our language in an interface. We pass this interface to describe the operational semantic, and to define our interpreter, we define the context based on the fragment you want to compose. The question is, one of the advantages of Tagless final in general is that it's fairly easy to define a staging interpreter for a DSL that is built via Tagless final. Does our approach still allows it? Fortunately, yes. So the only thing that we have to do is to use alab of A here instead of alab, and the definition of the implementation of the language fragment are quite straightforward. It's quite straightforward, but when I first do the test of this implementation, I have a little surprise, because when I test on this expression, so it's basically lambda x plus the read expression plus 5, I expect to resolve the read expression when I try to run the GLab and to perform the addition at compile time. And unfortunately, when I just look at what Idris has compiled, I see that the addition wasn't performed. And the issue is that, unfortunately, the lambda abstraction stops the interpretation of the subterms. The good thing is that we can do some kind of term rewriting using some interpretation of the different language fragment, and by providing an interpreter that will do the term rewriting for us. How do we do this? We provide an interpreter that operates only on RAID and base, and we provide a way to choose between this interpreter and the initial one, depending on the expression to interpret. So we do the full exercise of providing an interpreter again, only for read and base language. And this time, we will return A and an alab of A at the same time. And now we have to relate this interpreter to the interpreter of the three language fragments. To do so, we need to relate the context, so the wider context, the one that contains the list of variable and the read and the type of the read information, with the narrower context, the one that only contains the read information. So we define this interface that generalizes this issue, and we define this relation between the two contexts to say that this context can be projected into this one. So if I have as a context for my wider interpreter R and a set of variables, if I just want to give it to the interpreter that isn't interested into the variable, I will only have R. This way I can implement my implementation of embed, why am okay. No, yeah, okay. So this way I can just establish the relation between the initial interpreter and the interpreter for read and base only. And now I can build another interpreter that will rely on two interpreters, the big one and the narrower one. And I have two constructors for this interpreter, one that will carry along the initial one, the wider interpreter, and one that will carry the more specialized one. And no, I only have to implement my three language fragment for delegate. And this is what I do here. So in the base case, I just carry along, in the case of int, I just use the delegate interpreter. In the case of addition and multiplication, for example, I will rely on this function, and this function just try to use delegate as much as it can, so the more specific interpreter as much as it can. And when it can't, because one of the two subterms rely on some language fragments that are out of the scope of my narrow interpreter, I go back to the wider interpreter. And using delegate, I'm now able to perform the computation of the subterm as I expected to. As a conclusion, so regarding dependent tagless funnel, it is a composition of fragments that require different contextual information. It doesn't impact the staging capabilities, and it is the specialization of an interpreter. But there are some limitations. Building reusable expression is still cumbersome. So if I build an expression for a given interpreter, it's quite easy to build something. But as soon as I want to be generic and to say, for example, that I want to build an expression for anything that belongs to the base and the read language and whatever fragment I want to add to this, it becomes quite cumbersome to deal with it because I will need to do some kind of term rewriting in Idris, and it's quite painful. The reusability of interpreter is still an issue as well, because when I have an interpreter for a set of fragments, if I want to add fragment to it, usually it will be hard to reuse the existing interpreter. And there's a trade-off to find between the reusability and the complexity of expressions that is hard to find. And that's it. So we can move to question if you have some. Thank you.
Thank you. Thank you, Nicolas. So do you have any questions? So I know of a language that also has a form of dependent types and quantitative types, which is called Granule. Have you looked at that language?
No. What was the name again?
Granule.
No.
I'll send a link to you later.
Oh, yeah.
Yeah. I was wondering if all of this can be done in that language as well.
I think so. I mean, there's some specificities of Idris that I use in this implementation, but as soon as you are able to make the distinction between the type level manipulation that you will have into your language and the language itself, and to relate the two, the implementation should be doable, I think.
Okay. Yeah, my guess is that I'm not familiar with Granule language, but perhaps the dependent types are not fully supported in that language. So yeah, that depends on how much full dependent types you need for your implementation.
That's an issue, actually. Yes, I think that we don't use a lot of dependent types in this specific part of our work. So I think it should be doable, because at the beginning, I almost think about doing it in Haskell, actually. With some of the language of the dependent type extensions that are available in Haskell, like type families and all this thing. But the thing is that it's by far more easier to do it in Idris, because it's a lot less cumbersome to do this thing than having to deal with type families and the way that dependent types are added to Haskell. So having it natively makes it by far more easier to implement, definitely.
Thank you. Any questions from the audience? No? So in your paper, you supported a single effect, which is the read effect.
Yeah.
So I was wondering if this approach scales to other effects as well, like non-determinism, exceptions, and
exceptions, it's quite hard to think about, because the way we use tagless final is, at least in our work, is definitely to keep most of the effects out of the definition of the language and to introduce them when we build the interpreters. So I think that the approach will scale quite well as soon as, well, the effects that you add just add something to the context. So basically, if you want to add state to the stack of effects, if you non-determinism should work as well, I think. But for exception, I don't know. We should try to do it, actually, to see whether it's possible or not.
Yeah, that might be an interesting direction for future work.
Yeah.
Okay, so no question from the audience? In that case, let's thank the speaker again.